here, and good morning, everyone, and welcome again to our class. So we're now beginning our final topic, which is on the Z transform today, and we're in the final stretch. We are in week 10 now, and hopefully with everything being done, we will be able to finish this topic by next week. So we have some time to review and to revise and have some space to go over any things that might be, still in people. Do questions specifically asked to use words? Yes, just check some of the past papers that are posted already, and you'll see the kind of questions that are usually asked in the exams. Yeah. All right, and as I told you, with that particular technique, the thing like the block diagrams use plenty paper, and that is one of them that until you have the final, well, once you settle with the final exams, maybe it's not a bad. Sorry, once you settle on the final answer, maybe it's not a bad thing to write some of the calculations in pencil, and then once you have it correct, kind of correct it over if you want. All right, just now, half a second. Right. So when you're recording for this lecture, you're going to have a little blank here just for that. Sorry about that. Okay, so let's start here, and we're going to talk, we're introducing discrete time systems, and specifically the Z transform this morning. And a nice way to introduce this is to think about repaying a loan. And you'll see where that sort of connects up to everything in a little while. I'm sure a few of you are in situations where you may have taken a loan and you have to repay it. And if you remember, the arithmetic behind it is fairly straightforward. So you take an amount, and we'll just follow it through. You take an amount, of course, and we'll call that amount Y0, which is the initial amount. And then you're going to pay at some periodic interval. So let's say we're going to pay every month, right? So K will be what we're counting, the sort of number, the index that we're using to count. And at the end of each month is when the payment will come out. So at the end of a particular month, you pay some amount X, right? So XK will be the amount that you pay at the end of the kth month of the loan, right? And we are assuming that you're paying the same amount every month. The interest is I is the interest per year. So this is over a 12-month period. And then at the end of any particular month, the amount that you owe is Y K, Y sub, well, in brackets K. Okay? So at the end of month 1, you start off, Y0 is what you owe. And then what the banks do is that, of course, during that month, they're going to add the interest for the month, which is 1/12 of I by whatever you owe at the beginning of the month. So by the time month 1 comes to an end, right, you started off owing this. Let me just, so you started off owing this. They slapped on some interest for you. So now the amount that you owe is now Y0 plus some interest. And then you make a payment, right? And once you make the payment, now your fixed amount, whatever that is. So what you owe minus your payment is what you're left with at the end of month 1. And then, of course, we proceed to month 2, and the same thing happens. Month 2, you start off with what you were left with at the end of month, tack on the interest, and minus the payment for month 2. And you're now left with that. So similarly for month 3, it will be y3 here, right? It will be y2 here, y2 here, and x3 at that point in time, right? So there's a pattern developing here. And so that at any point in time now, any month, any arbitrary month during the period of the loan, what you owe at the end of the month is where you were at the end of the previous month plus the interest that you accrued during that month minus the payment. We call this a first order difference equation, right? We'll see where the first order bit comes about, but largely it is because the current amount is just a function of 1 month before, or one, if you look at it and forget the payments itself, one value here, the current value, is just a function of the immediate past value, one behind. So it's a second order difference equation. If we had a yk minus 2 anywhere inside of there, then this would have become a second order difference equation. Yeah? Nothing too strange about that. So in continuous time, we have, well, I'm saying we had, but we have a differential equation. So a first order differential equation is where you have the first order derivative of y and x in there, right? You may or may not have the first order derivative of x, but for a first order differential equation where we're dealing with y as the output, for it to be a first order differential equation, we have to have at least a dy dt in here. And you solve it by, first off, you had to get the initial conditions. In other words, what was the system or whatever made that equation, what was it doing at the start, and then you solve it. So the same thing is a difference equation, that what you have to do is to find, like in a differential equation, we're trying to find yt in terms of everything else plus the initial conditions. The same thing when you meet a difference equation is that you're trying to solve y in terms of everything else. The main difference is that we are dealing with discrete time. The continuous time would be a function of the continuous time variable. The discrete time solutions and answer is a function of fixed values in time, right? Remember going back, way back when we talked about discrete time systems, remember they only exist at particular intervals, right? So you sample the system, or you sample whatever it is at time, at some interval t. So you get values at the first t equal to 1, then at 2t, 3t, and 4t. But you never have anything in between. So the only picture that you have are the values that occur at some integer multiples of t. Right? So that's a little revision there. So going back to our difference equation, how you solve the difference equation basically is that you look at it, and if you look at, for instance, the payment for month 2, we have y1 in there, and we know what y1 is from before because we just worked out that. So I could substitute for y1 into the equation for y2 and get this particular thing. So I'm starting to get an answer for y in terms of y0, which is the initial condition of the of whatever it is that created this. In our case, it's a simple loan. And then you keep going doing that, and you can see the pattern here already. You could just watch it and see that the pattern for the solution is that the answer, which is going to be a general answer in terms of yk, so that now I could determine y at any point, just pick a value for k, is going to be yk is whatever is the initial value of this thing. We have this 1 plus I over 12 bit, and that is going to be, notice the index, you can see the pattern, right? So this one is sort of solving by observation, if you like, looking for a pattern. So this is going to be a key. And then you have this starting with x, k minus 1 into this. So the general form, the pattern is going to look, the answer is going to look something like this. So this is my general output. This is my initial condition, and the xi's are my inputs. Yeah, fair enough? I mean, it's just pattern observing here, right? And there's things that you would have done in back in high school. Of course, there are more formal ways to do it as you get more complicated. And I think you also may have done some of this thing in ECNG 2013, I think, in discrete math, right? If that's still part of the course. So that now, getting to that is referred to finding the solution by recursion. In other words, you repeatedly substitute a known answer back into what you have, and then you substitute again until eventually the answer or a pattern emerges from what you have, and then you have the final general solution. This is like when you were solving a differential equation. You remember, to solve a differential equation, you have to integrate. And what you do is that you integrate, and then you look for the initial conditions, and then you look for patterns relating the yt and the dy dt and so on. If the patterns are straightforward, then you could get something called an integrating factor, and you eventually get a solution, a general form of the solution, right? So at this point in time, I could pick any month, k equal to 15, for instance. Now, oops, 1, 5, right? And if I substitute in here now, I could get y15 in terms of everything else, right? And then just a little comment here. Notice that if, and this for you in your life going forward, that if you're paying less than the interest, then your loan never going to be paid off, because basically what happens is that it's going to accumulate faster than you could pay, right? So always remember that. Always, when you take a loan or when you owe anything in life, you have to pay it off faster than it's accumulating interest. Yeah, yeah. Otherwise, well, time will catch up with you. So back to this thing. Discrete time systems are modeled, in fact, using difference equations. So the continuous time world used differential equations. The continuous time domain, or sorry, the discrete time domain is going to be modeled using difference equations. And a discrete time system, the model is like that. That is, you have the system, the inputs to the system is a sequence of numbers. So xn is going to be some values, 1.75, 3 by 10 to the 6, etc. It could be any kind of random funny thing, right? But it is a series of numbers. The numbers, and remember this xn, oops, just shrink this back a little bit. The xn is really xnt, right? And t is the sampling period. So whatever produced xn or xnt happen every t, whatever that may be. It could be every microsecond, it could be every millisecond, it could be like a stock market, every minute, it could be every hour, it could be every day. You don't care. The only thing is that the system sees a set of numbers coming in. It is designed to handle the series of numbers coming in like that because it knows what t is. All right, so the system response, the system input is a sequence of numbers. It is going to see that coming in, and it is going to respond and give you another series of numbers coming out. Remember, in the continuous time domain, if xt was going in and ht was the system transfer function or the system response, that the output was the convolution of x and h. The same thing actually happens here, that yn is in fact the convolution of xn and hn. And remember, we spoke about that even without talking about difference equations. We spoke about that when we introduced the whole idea of convolution way back in lecture 10 a few weeks ago. Right? I hope you recall. So in a discrete time system, and good thing for us, the discrete time system takes numbers in, it churns around the numbers and gives us numbers out. Right? You're not going to get a continuous signal coming out of a discrete time system. And similarly, you can't put a continuous time signal into a discrete time system, okay? You have to go from one to the other. And now that is where the topic that Dr. Radek spoke about is that if I, on the front end here, for instance now, if I had an xt that had to go here, then I have to do the sampling and the conversion to get it to that number. So you're going to have the sampling and the overall analog to digital conversion. In other words, you're going to take the continuous time and convert it to numbers. And then if yn comes out here, you're going to go into the digital to analog conversion back part, and then you're going to get yt here. And remember, she mentioned before that the yt that you're going to get here is in fact something called an estimate. That's why I put a little hat on it. This is a little bit different than the real yt. So if xt was supposed to give you a real continuous yt coming out, if you pass it through a discrete time system, you're going to get a yt coming out that is an approximation of what the real answer is going to be in the continuous time domain. But if you're careful and you design it properly using proper techniques and so on, the answer that you're going to get is going to be, for all intents and purposes, the real answer. And this is where they work in control system design, that you're going to meet some of that next semester. And then if you decide to specialize in things like control and or communication, you're going to see how they analyze those sorts of errors or the differences between this estimate and what the real thing is supposed to be, to make sure to minimize that that sort of difference. Yeah. And you're going to have, well, that's the advanced work. This is just a foundation to introduce this stuff, but the advanced work is very specific to the particular topic that you're dealing with. Yeah. So if you remember when you were going back in and the first time you did differentials and derivatives and so on back in your calculus days, your admaths days, which seems so long ago, you remember that to get the derivative of a curve, how it started off was first finding the slope. How do I find the slope of a curve? And the slope, of course, was the tangent at some point. What you did from first principles was that you had the curve, so you were given the curve, and you took 2 points on the curve, and you drew a straight line between them, those points, and then you estimated you looked at the gradient of the curve, of the straight line, sorry, and the gradient, of course, was the interval y over x. And then what you did was to make this interval get closer and closer and eventually become very small, so that the line at that point became the tangent to the curve. And this is what you learned it as. So dy dt was in fact the limit of these 2 points separated on the curve by a very small space. So the difference in y over the difference in x, as that difference in x got very, very small. All right. And then, of course, then you learn how to do the actual calculus manipulation and so on. So if you think about what happens now when you discretize a system, or when you convert something from analog or the continuous time domain, sorry, to the discrete time domain, what you do is that you sample it. So that in our case, with the curve, we never would have had the actual curve. What you would have is that you actually would have two values, that is all you know. You have no idea what goes inside, so what goes in between those 2 points, so that your estimate of the slope of that, whatever is passing through those 2 points, is this expression here. You have yn plus 1, right? And I'm leaving out the t, right? You know that that has occurred in is multiples of capital T. So you have the value at yn plus 1. You have the value at yn. So you take the difference, and the spacing was one sample period. You have nothing else in between. So that dy dt approximately is yn plus 1 minus yn over t. So that you could, now you see now that the equivalent now, so that for the continuous time differential equation, where we had dy dt, in the equivalent discrete time version, instead of a dy dt, we're going to have that yn plus 1 minus yn over t. Make sense? And of course, everybody remember here that yn is really yn t. Remember, the discrete time world only happens at intervals of t, right? T, 2t, 3t, 4t, 5t, and so on. There's no t.5, 1.3t, that kind of thing. Okay, it doesn't, and get it in your mind that the discrete time world assumes nothing between the two values. So it will see the value y1, it will see the value y2, or in this case, it will see the value yn plus 1, it will see the value yn, and that is all it will work on. It makes no assumption of anything in between, because it does not know. Those values don't exist. It never sees it. Yeah? So once you do that now, of course, if you rearrange the equation now, you get it back into this form, which is our first order difference equation. And you notice, and we'll meet this a little bit later on in the Z transform lectures, this, I could move around this and basically shift the signs around a little bit. So I could also have, once we're dealing with the linear time invariant systems as we have been, I can write this over as yn equal t x n minus 1 plus y n minus 1 into 1 plus at. Right? Both of them are the same. All I've done is to shift it around by one sample. Right? In other words, the difference equation for the one capital T ago would be the equation in red there. I haven't done anything because it's linear time invariant, right? Yeah? Make sense? So you can move it around, which is a little bit different than what you would be able to do in the continuous time domain. But here you're dealing with numbers and samples, so you can shift it around a little bit. It's just a sequence of numbers. And you solve this. So to solve, can you, okay. Yes, Hakim. So you understand, we came up with the equation in blue. And what I'm saying is that if that one time, one capital T, whatever that interval is ago, that the difference equation would have been, if this is the general form that I have with the blue tick, that yn, which is 1t ago, right, would be tx n minus 1 plus yn minus 1 into 1 plus a. Notice that both equations are the same. All I've done is to decrement t by 1. In other words, go 1 period or go. If I add 1 to the red, then I get back the blue. Yeah, I'm just shifting in time by 1 capital T. That's all. Yeah. So x and just hold on. Let me see that question, Sadie. 1 second. The previous slide. Go back here. What about the previous slide? Xn t minus xn plus 2t. Well, your question is correct. Would be a period of 2t for the denominator. But I'm not seeing that here. I said, yeah, I'm not seeing that on the previous slide. Right, we were deriving, remember the derivative is one time period. dy dt and the equivalent is just over 1t, not 2. Yeah? And remember why t was under, no. T is not understood to be 1. T is t. T could be anything. T could be microseconds, it could be milliseconds, but t, as you go from t to t plus 1, it means this is really n plus 1 t. In other words, I'm incrementing. So whatever, if I had t, then 2t, then 3t, etc. Right? T is being incremented by one number, one integer all the time. So the only values like these, this is really yn plus 1 at time t. The next one would be n plus 2t, n plus 3t, etc. All right? Make sense? Remember the discrete time? Yeah, it's like, okay, it's like, just for argument's sake, the weather report, right? So every night, if you listen to news or something, so to hear the weather, you're going to hear what the weather, what the temperature at the airport was at a particular time today. They're not telling you what it is now. They're not telling you what it was 6 o'clock in the morning. So at 1 p.m. today, the temperature will be 34 degrees. At 1 p.m. yesterday, it was 35. And if that is all that you have, your yn would have been 35, which is yesterday. Your yn plus 1 will be today, which is 34. Yn plus 2 will be tomorrow, which is whatever, 37, and that kind of thing. There's nothing in between. None of that data will tell you what y at 6 p.m. for argument would have been. Fair enough? Yeah? Right, and you have to think about it in that context, that the discrete time system only exists and calculates these values at particular intervals in time. So back to this, there is one that we have here. If you look at this, the solution to this, how you would solve it is that you get y1 and you substitute, and then you get y2 by substituting for y0 and y1, and so you keep going until eventually you get some kind of pattern for yk. And this would be your solution. So this is the general solution for that difference equation, and you solve it by recursion. And as I said, you would have some of them you would have met these kind of things already in your math. And then in discrete math and so on, there are more formal ways to solve. And in fact, difference equations, there's a whole set of mathematics around difference equations, just like there's a whole set of mathematics around differential equations. But in our case, we are engineers, right? We could work with the math. We could work with the math and so on if we have to. But our job and our careers and what we like to do is to fix things and solve problems. So you don't have to spend too much time solving difference equations by recursion and unless you absolutely have to. You could, but you don't want to, right? So we will come up with a better way to do that. And then just look at it a little bit, the behavior of the difference equation, that the form of it is that the next output is a function of the current input and the last output. Notice this is, you have done this, or you should be doing it in your sequential logic. Well, when you talk about sequential logic problems and so on, and maybe you have met it already, I'm not too sure. Things like Mealy, ALY, and more, right? Mealy and more systems. Have you met that in your logic, in your sequential logic? State machines, exactly, right? So the state machine, the function of a state machine, the next state, some of them is a function of the current input and the system, some of them are a function of the current input, the last output, and the system itself, right? Many sequential, and if you think about it, what is a sequential system? The sequential logic systems and state machines that you all have met are actually, they're working on ones and zeros. There's a clock in there that will change it every t, whatever the clock period is. So every t in intervals, it will change depending on what the values of the various registers are. So in fact, a sequential machine, the description for it is in fact a difference equation. So when you write out a logic equation, that is a form of a difference equation as well. It happens to be that the ones and zeros inside of there, if you're working with actual electronics, will be 0 to 5 volts or 0 to 3.3 volts or something like that. Okay, but that is a perfect example of a difference equation implemented in circuitry. Yeah, so you met it already. Right, so your frequency meter, yeah, is based on that sort of design, exactly. Right, so what you're doing without even thinking about it is that you are working with a difference equation and manipulating difference equations there. Right, so it's in the background. And this, again, just for our purposes, the general form for single input, single output difference equation is that form that we have here, right? So single input is X, single output is Y, and the next output is a function of the past outputs and the current inputs, right? So, right, and as we say, N is the order of the system itself. So if I have that I'm dealing that my next output has to do with KT minus 3T, for argument's sake, then that is a third order system and a fourth order system and a fifth order system and so on. You're not going to meet it here, but if you ever do discrete signal processing, it's not unusual to have systems whose orders are all 50 to 100, right? You're never going to meet a 50 order continuous time equation, right? So you're never going to, in continuous time, you're never going to see d50 y dt to the power 50 ever, right? You're lucky if you even see d cubed y over d cubed, d3y over dt cubed. But in the discrete time domain, it is not unusual to see 50 order and 100 order systems quite regularly, because it's just numbers you're dealing with, and manipulating numbers is what we're doing here. Logic systems and computers, they're designed to do that, right? The order of the system, no, absolutely not. It doesn't change every time you sample, right? The order of the system is fixed. And in fact, the order of the system is largely determined by how you take the sample. So if you go back here, right? So for instance, this one y kt minus 3, minus nt. Whatever n turns out, I put a value here of 3, is determined by the design of it. So you will know from whatever it is, like your, let's go back to your state machines, for instance. If you're dealing with something that is a shift register, for instance, a 4-bit shift register, is going to store values going back at least 4 clock cycles if it's 4 bits, right? So that the system itself determines the order. How many, again, like in the shift register or in a counter, how many bits of the counter determines the order of the system, right? So that's not going to change every time you sample. Every time you sample, again, back to the shift register, it changes every time it quote unquote samples is every clock interval. So every time the clock changes, the shift register will change. But you're not going to change the clocking at all, right? It's clock once, clock twice, clock 3 times, etc. in a sequential way, right? So the same thing, when you have a discrete time system, the order is not going to change every time you put a sample into it. Fair enough? If you do that, then you're not dealing with a linear time invariant system. It wouldn't be time invariant. Fair enough, Hakim? Yeah? Right. Okay, so if this particular system, let me just clear this on the screen here. If I start at time equal to 0, in other words, I deal with just, what do you call it, a causal system, then that big equation will just condense into the form that we have here, right? So the output at time nt is a function of the input at some time m, and I deliberately have the indices for n and m different because, remember, as I told you, discrete time systems, because you're dealing with numbers and because you can, you remember way back when we said, because you're dealing with numbers and because you can store number values, as you know now in files and the like, you can actually have a discrete time system that is not causal because you could jump into it. And the great example I gave is that you could a tune that you're streaming online, for instance. You could save it and you could jump into the middle of it, or you're watching a video, you could jump into the middle of it. At the point when you jump in, it has stuff that existed before you started to look at it. In other words, it is not causal. And what you're seeing or hearing at a particular point in time depends on what went before. So it is not causal. So discrete time systems can be non-causal. And there's just a little question here that if m and n, m is the output at time, sorry, n is the index of the output numbers, m is the index of the input numbers. If the system is causal, there's a relationship between m and n. And the actual thing is that m, which is the input, has the index m has to be less than or equal to n for the system to be causal. And you could prove that. It's a little bit of just thinking on a logical side, but think about it and verify for yourself that m has to be less than or equal to n for it to be causal. Yeah? Make sense? Any questions? All right. So it is, I wouldn't start the, I mean, it's 8:46. So it doesn't make sense starting the actual Z transform topic right now. We'll do that tomorrow, please God. The lecture is already up, so you could have a look at it. What I wanted to, because I realize that some of you all, again, it's unusual thinking in the discrete domain as compared to all of our many days of thinking about continuous time and discrete time, continuous time functions and so on, right? We spent a lot of time doing that, and most of your dealing with anything engineering has been in the continuous time domain. The one exception, of course, is your digital electronics and things like your sequential and state machines, your sequential logic, and so on. And that, in fact, is an excellent way to kind of get your hand on get your head around what we've just discussed here. Think about it in terms of maybe a simple flip-flop, like a type D flip-flop, right? What it is the type D do, it takes the input and puts it at the output, or it takes whatever is on the D input and put it on the Q every time you clock, right? Every time they clock, either it's a level or edge trigger, but as the clock changes, it takes D and puts it on Q. So D is a current input, Q is the output, right? Does it depend, does Q depend on what D is? No, unless you feed it back, right? D and Q are two totally dependent things. So it will just repeat whatever D is will appear on Q. If you put two flip-flops in cascade, now you have a different situation. And when you clock the flip-flop, what goes from one to the other is a function of the current state. But it's not going to change in between. It's only changing at intervals of the clock. So if you think of the interval as T, 2T, 3T, 4T, etc., it is only at that point in time that any change in the flip-flop will occur. It doesn't do anything in between. The same thing for a discrete time system. So once you have a discrete time system, right, which is the H N T, this only responds. So a number comes in, let's say the number 7, it does something. It does something and give you a number 9 coming out, right? Just for argument's sake, if T was every 1 second, right? So number 7 comes in at T equal to 0, 9 goes out. Nothing happens until the next point, which is at 2 seconds. 2 seconds, it looks and see 5 coming in, and it gives me 4 going out. Nothing will happen until 3 seconds. Then it will look and see what comes in and give me something coming out. If something was to come in at T equal to 1.5, it would ignore it, right? It can't work that way. It will only respond every T. And all it is responding to is values. Certain values. These could be anything, but they are values, numbers. In other words, something tangible comes in, it will do whatever it needs to do with that until the next time you tell it to work again, which is at intervals of T. Okay? That is how a discrete time system works. And the mathematical description of that is this thing called a difference equation. So that if you want to predict now at T equal to 48 seconds, what would the output be if I were to give it an input of 10? What would the output be at T equal to 48? Then what you would have to do is to get the difference equation for this, plug the T equal to 48, the N equal to 48, T inside of there, and see what the output would be. But as we say in our neck of the woods, solving this by recursion is complex. So we're going to find a different way, and for our electrical engineering purposes, what is going, just like how the Laplace transform helped us to solve the linear differential equations, then we have a new transform, which is a Z transform, that is going to allow us to solve the linear difference equation. Yeah? And we will see the manipulations are very, very similar. There's a lot of commonality between it, but there are some differences, and this is the new things that we're going to spend some time on. Yeah? Fair enough? All right. So tomorrow, please God, we're going to look at the Z transform formally and see how it works. And then by that time, we'll be almost finish with what we have to do, and we'll have one other, it's basically three lectures on this air transform that we're going to do, plus of course the problem set and past paper questions on it. So think about this. You also have the stability lectures to review as well. Okay, so you have three sets of things to look at in between, and I will see you then tomorrow afternoon at 1 p.m. So unless any questions at this point before we close off? Yeah, it was going to recordings. I mentioned that in the announcement. So go into the lecture recordings, and you will see it. You'll see two lectures. Funnily, both of them are under stability part 1, but you'll see recording 1 and 2. When will you receive the grades for your midterms? Well, hopefully sometime before you graduate, right? So actually I'm working on it. So you'll get it shortly. All right. Yeah, hopefully before then. Yeah. Maybe. Anyway. All right, folks. So I will see you all, well, in this class tomorrow, but I'll see most of you all hopefully this afternoon at 3 p.m. So take care, everyone.